Welcome to EDU World Space.
Let's take a look at a chemical reaction and see how it might be affected, or its Gibbs free energy might be affected by temperature. And so if we take some NO2 and some N2O and make some NO, we want to know what is the effect of temperature on the Gibbs free energy of this. Well, to be able to do that, if we want to know how that's going to be affected, what we need to do is calculate the delta H's and the delta S's of reaction for this and be able to do that. So if you recall, the delta H of reaction is going to be equal to the sum of the number of moles of the enthalpy of formation for the products minus the sum of the number of moles times the heat of formation for the reactants. Same thing for the entropies. So we're going to use this equation to be able to figure out the H and the S for each of these, and then be able to look at that in terms of delta G. So when we go and do that for the enthalpy of reaction first, under standard conditions, what we have, because remember we do products minus reactants, is we have 3 moles, and each delta H is 90.37 kilojoules per mole. And then we have 2 reactants. We have NO2, which has a value of 33.84 kilojoules per mole. And we have to do the same thing for NO2, which is going to have a value of 81.6 kilojoules per mole. And so when we do the math on that, we're going to find that the enthalpy of reaction is 155.7 kilojoules. And when we go do the delta S, we'll go get those values, and we've got 3 moles of NO. Each has an enthalpy of 110.62. That's our only product. So then we go subtract the reactants. We have 1 mole of NO2 at 240.45. And we have 1 mole of N2O at times 220.0. And when we go do the delta S of reaction, we're going to find that the enthalpy is 171.4 joules per Kelvin. And if we convert that into kilojoules per Kelvin, that's 0.1714 kilojoules per Kelvin. All right, so what does this tell us? So now that we have the values that we need, what does this tell us about the Gibbs free energy? So remember, Gibbs free energy is equal to delta H minus T delta S. Well, we have a positive delta H, we have a positive delta S. That means that this negative T delta S term, remember temperatures are always positive because in the Kelvin scale, we need to get this negative term low enough, or we have to have the temperature high enough to turn this term more negative than the delta H to get a negative delta G. So this tells us that we're going to have a spontaneous reaction at high temperature. Now, what temperature is that? Well, we don't know what temperature that is. But let's take a look at a couple of examples and see if we can figure that out. And so let's see what happens at 800, and let's see what happens at 1,000 Kelvin. And we're going to use the values that we had from before. We're going to use also the same equation. Now, we don't have a naught because we're not at 298 Kelvin anymore. We're at either 800 or 1,000. So when we're going to look at 800 Kelvin, we're going to go and get our values of delta H and delta S and go ahead and plug into Gibbs free energy. And so we have our 155.7 kilojoules. We're told it's at 800 Kelvin, so minus 800 Kelvin. And the delta S in kilojoules per Kelvin is 0.1714 kilojoules per Kelvin. And so we find that at 800 degrees Celsius, the delta G is going to be 19 kilojoules. That's not spontaneous because it is not negative, because it's positive. But what happens when we get to 1,000 Kelvin? So when we go and do the same reaction, same equation, same numbers except the temperature, we have 1,000 Kelvin this time. Well, when we do the math this time, we find that we get a value that is negative 15.7 kilojoules. Well, that's negative, so that is spontaneous. So when we got to a high enough temperature, some temperature between 800 and 1,000 degrees, that is the temperature at which the reaction will be spontaneous.